So that's how we can get our acyl chlorides to be converted to another derivative. If we wanted to do a conversion of a acyl chlorides in such like a reduction reaction, a reduction reaction would substitute the acyl chloride for a hydrogen or a carbon group. We're going to go through those now. Three main ways to do that. Lithium aluminum hydride. We'll take an acyl chloride and make it an alcohol. We're going to go through that. It makes it a primary alcohol because lithium aluminum hydride is so reactive. Again, lithium would be a plus charge. Aluminum holds a minus charge, and for hydrogens, hydride comes, attacks the carbon of the carbonyl, makes the tetrahedral intermediate. We first do a substitution reaction. Oxygen would roll its electrons back down to make an aldehyde. Cl- is an excellent leaving group, just like we saw in the previous 4 reactions. Lithium aluminum hydride cannot stop reacting though. So a second equivalent of lithium aluminum hydride reacts just like what we saw in chapter 19 to an aldehyde. It will add, forming that tetrahedral intermediate. And that's when we move on to the last step, the water or the acid workup. Oxygen can get protonated and form our primary alcohol. If you wanted to stop short at the aldehyde, we cannot use lithium aluminum hydride. You cannot stop here because lithium aluminum hydride is such a strong reducing agent. If you wanted to use a weaker reducing agent to stop at the aldehyde, the best choice is going to be a lithium tritert-butoxy aluminum hydride. That is a mouthful. It is a lithium aluminum hydride reagent with simply 3 oxygen ether groups and 1 hydrogen. What that does is it reduces the reactivity and therefore stops the reaction at the aldehyde. Helpful. Mechanistically, the exact same as the very first step, just stops at the aldehyde. Last one that I want to go over, how do acyl chlorides react with Grignard reagents? If we have a Grignard reagent, again, what is going to be happening here in this reaction? Again, we should see our Grignard reagent up at the top, followed by a water workup. Typically for that Grignard reagent, we see excess, right? Excess, not extra small, excess, it's just an abbreviation, often used by organic chemists. Not extra small, it's not a t-shirt size, it means XS. Just say it really fast. And what happens is we do form alcohols and we add 2 equivalents of Grignard reagent to our final product. Let's go through that mechanism. Again, a Grignard is going to be a carbon nucleophile. Carbon will add onto the carbon of the carbonyl, forming that tetrahedral intermediate. The first product is going to be that of a ketone. Once the chlorine is substituted. Nice. Can't stop, won't stop. We'll add a second equivalent of our Grignard from what we know from chapter 18. Ketones react with Grignards. And then we'll do our water or our acid workup to protonate our alcohol. So we end up making tertiary alcohols with this Grignard reagent. So just in summary, we see a variety of reagents here. The only reagent that we're going to hold off on is the cuprate. Cuprates we will talk about a little bit later in chapter 21. Cuprates are weaker organometallic reagents, and so no mechanism for that yet, but a cuprate is something that will react similar to a Grignard. It is a carbon nucleophile, but it stops at aldehydes and ketones. They do not react with aldehydes or ketones. So they can react once and do a substitution reaction, but they do not continue to do the addition reaction. Very, very similar to the use of the lithium derivative that is the more mild hydride reagent. This is the mild hydride reagent. This is our mild carbon or carbanion reagent. All right, preparation of anhydrides. Now, anhydrides can be synthesized by excessive heat of the carboxylic acid. This only works for acetic acid though, so it's not something that you would most likely see on an exam. What we want to be able to think about is for our reactions of anhydrides, what can we actually do? Well, we can take an anhydride through a couple of different reactions. We are only going to show 2. Now that is primarily because when we think about, or I guess there's 3 because the oxygen, there's gonna be 3. When we think about acid chlorides can become anhydrides, but anhydrides cannot go backwards to become acyl chlorides. So here's an example. We'll just get rid of R groups for now. Let's have a very simple acid anhydride that is symmetrical. We can use water and we will form the carboxylic acid. Let's go ahead and walk through the mechanism. Oxygen attacks one of the carbons of the carbonyl. Doesn't matter which one, choose one, they're the same. We would always keep symmetry in this reaction. So either will work. All right, now we're going to use the second equivalent of water to be a proton transfer reagent. And that proton transfer is going to, take the proton away from what was the nucleophile and give it to the oxygen sandwiched in the anhydride. Most likely this does not occur via an intramolecular proton transfer simply because these oxygens are too close to do an intramolecular reaction. So we use water as a sort of a funnel. Then our oxygen can kick out the 2 carboxylic acids, right? We have 1 carboxylic acid here and a second carboxylic acid here. So even if the molecule is not symmetrical, you still get 2 carboxylic acids. If they were symmetrical, if the anhydride is symmetrical, then just draw 1, right? No repetition necessary. That same exact reaction mechanism can be done with alcohols as well. And what happens with the alcohol mechanism is we make an alcohol and a carboxylic acid gets kicked off as well. So carboxylic acids or esters can be produced just by throwing in that anhydride. Beautiful. Last one on this section of substitution, the anhydride can be reacted with an amine. Could be, again, ammonia, a primary amine, or a secondary amine, and that will result in an amide. Let's do the mechanism. Nitrogen, again, a base, attacks the carbon of the carbonyl, kicks up the lone pair. I'm going to hang off one proton this time just to be a little bit quicker. A second equivalent of the amine will come in and deprotonate. The nitrogen, so it's neutral. We do not, on this reaction, need to protonate the oxygen because nitrogen is more basic than oxygen. Nitrogen holds a positive charge better. Oxygen holds a negative charge better. So we kick out a carboxylate ion, and we're left with the amide. Excellent. Now, again, we can use lithium aluminum hydride in order to react with an ester, and that would react the exact same way. So I'm just going to write that reaction here. And again, you can use a mild version to stop at the aldehyde. If you use lithium aluminum hydride, you are going to get two equivalents of hydrogen added, and so therefore you will get the primary alcohol. If you want to stop at the aldehyde, just like we did with the variant for the acyl chloride, the variant for our ester, or our the variant for our anhydrides is the same. It's the lithium aluminum with our 3 ether groups attached, followed by a water workup. And that will get us to stop at the aldehyde. We can also use Grignard reagents on our acid anhydrides. Just like before, a Grignard reagent would act twice to make primary alcohols and add 2 equivalents of that R group. Again, cuprates can react as well, so we can see those also add just 1 equivalent of R group. We'll talk about cuprates again more specifically in chapter 21. The only reaction that we are kind of avoiding here that I didn't primarily talk about is this one. And that's because this is simply a deprotonation of a carboxylic acid with NaOH, followed up with an acyl chloride reaction of a carboxylate ion. So we already did that one. Notice the repetition there in the preparation of our anhydrides. Reactions of anhydrides can be used commercially, right? That's actually how we synthesize aspirin and Tylenol. Structures here, right? Making the ester or the amide, depending on which choice. Okay, let's move on to esters. As we get further on our flow chart, as we get further down the list of reactivity, we saw the most reactions were with our acyl chlorides, quite a bit of reactions with our acid anhydrides, but a few less than the acyl chlorides. Reactions of esters are going to have even less. We'll start with preparation of esters just as a review kind of idea, and then we'll get into their reactions. Esters can be prepared by an SN2 reaction. The SN2 reaction with specifically the carboxylate ion. So again, in step number 1 here, NaOH is going to deprotonate that carboxylic acid. And then we should be using a methyl halide or a primary alkyl halide, and that would undergo an SN2 reaction, which we have actually seen from chapter 7. All right. NaOH is used to deprotonate the carboxylic acid because, again, the pKa's are favorable. Fischer esterification combines the carboxylic acid and an alcohol. So using an acid catalyst, so we'd have to have acid conditions. Typically, the acids that we would see over the reaction arrow would be H2SO4 or TSOH. You can also simply just write H+. For this mechanism, you can use a protonated alcohol or you can use H3O+, just to be the proton transfer. We'll do that in the next slide, but notice here how the OH is going to be replaced with the ester, the ONE specifically in this example. So let's go ahead and walk through this. I'm showing, just as in the textbook, a protonated alcohol. Where we got that, if we take methanol and we add it to a strong acid like H2SO4, the reaction product is a protonated alcohol, just like we would see H3O+, right? It is an O+ here as well. Just one of those extra bonds is a carbon group, not a hydrogen. So that's what we're going to show. All right, so protonate the carbon of, or the oxygen of the carbonyl, similar to what we had done before in the previous chapter. What does this do? It makes the carbon of the electrophile more electrophilic. Now our weak nucleophile here, methanol, can come in and attack that carbon, kicking up a lone pair. That creates, again, a new carbon-oxygen bond and the tetrahedral intermediate. Now, a second equivalent of methanol will come in and deprotonate that nucleophile so that it is neutral. And then the oxygen of the carboxylic acid, OH, will get protonated. Again, do not do an intramolecular proton transfer. I know you're thinking, hey, Lauren, why can't we just go boop, boop, boop and grab that guy? Nope, that is too close. We do not see an intramolecular proton transfer occur unless there is 5-membered rings or 6-membered rings between the atoms, and this one would be 4, so not going to happen. Too strained, not going to be close enough together, because closer those two atoms are to each other, more steric hindrance. Okay, so we'll protonate that oxygen, which now becomes a leaving group. Roll the electrons back down, kick out water as the leaving group, and then in our final step, we will deprotonate the oxygen of the carbonyl. Now, again, same base nucleophilic attack and loss of leaving group that we've been doing, just a lot of extra peppered in proton transfers. So be very aware of these. The mechanism for Fischer esterification is supported by isotopic labeling. So there is a great way to understand why this mechanism works. It's because there is a radio label of the alcohol that can be done. That radio label of the alcohol oxygen is then found on the resulting ester. All right, so think about isotopic labeling as creating a little tag on our methanol reagent and then seeing at the end of the day, where did that little tag go? Because the oxygen is incorporated into the ester structure, that's how we have been able to prove this mechanism, and that water was kicked out, not keeping the same oxygen. This oxygen right here becomes this oxygen right here. Fischer esterification is an equilibrium process, so water must be removed to favor the formation of the ester. What that means is that we can actually do the reverse process, take an ester and react it with H3O+, and you'll get a carboxylic acid. We'll see that in just a second. One way to go backwards is basic, right? So the basic reaction is called saponification. An acid workup is necessary to obtain the neutral carboxylic acid because, again, after step number 1, we have a carboxylate ion because of the acidity of a carboxylic acid in a basic solution such as sodium hydroxide. We would always have that little last proton transfer be necessary to put the proton back on there. Mechanistically, it's basic, so we'll just see nucleophilic attack and loss of leaving group. Because of the pKa's, that's where we'll see that last little proton transfer at the end. So base or nucleophile attacks the carbon of the carbonyl, kicking up a lone pair. And then this is the equilibrium process. Either oxygen is fine to leave as a base. It is equilibrium, so expelling out the alkoxide ion as the leaving group just promotes us to make something different. But it's this that is actually driving the reaction forward, that alkoxide or hydroxide can come back and deprotonate that carboxylic acid because, again, the pKa is around 4 to 6, and the pKa of the resulting alcohol is around 16. So definitely a very good reaction to continue forward, which is why we also need that extra little acid workup, right? H3O+ will take this guy in a subsequent step and pop that lovely proton back on. Acid cleanup step. You can also hydrolyze esters under acidic conditions. This is what I was hinting towards. The mechanism would be the reverse of Fischer esterification, all right? Let's just walk through it relatively fast. The oxygen of the carbonyl is protonated, right? Then water is going to attack the carbon of the carbonyl. We can deprotonate that nucleophile so that it stays on. And then we will protonate the thing we want to kick out, which is our alcohol. And then we'll roll those electrons back down to kick out the methanol and use water or methanol to deprotonate. Beautiful. Those steps should be the exact opposite of what we were seeing previously. Reactions of esters, we can also undergo aminolysis to form amides, right? So overall, the equilibrium does favor the amide. Amides are more stable, less reactive than esters. So again, nitrogen is just a really good base, and so it's a really good nucleophile. Synthetic use is limited because this is very slow. It's more efficient to make an amide from an acyl chloride that we saw previously. A couple more that we want to go through is the reductions of esters. An ester can be reduced with lithium aluminum hydride. So let's go through that one. I'll just use OMe to show a very simple ester. Lithium aluminum hydride, same reaction as before, exact same, with the hydride reacting and a substitution to make it an aldehyde, and then subsequent addition to make two equivalents of hydride react to form a primary alcohol. So again, same exact reduction reaction that we saw in the previous sections with acid halides. We would do our substitution, right, to make the aldehyde, and then our addition to make the primary alcohol. Esters can also be stopped, just like we've seen before. They can be stopped with a less reactive reagent. That less reactive reagent is usually called diba-H or dibol-H. Sometimes there's an L in there. I'm going to write that one up. Depending on what textbook you use, sometimes written like that, diisobutyl aluminum hydride. I'm going to draw it right down here. Diisobutyl. Isobutyl is that group attached onto an aluminum. There's two of them, diisobutyl aluminum hydride. There's dibol-H. So what is this guy good for? Well, he's less reactive as a reducing agent, so he gets to stop at the aldehyde. Grignard reagents can also react with our esters. Same as before, we would see two equivalents of the Grignard reacting and a water workup. To add on two new R groups. This reaction and mechanism is the exact same as the acid chloride.